Okay, while we're waiting for people to finish up, because some of us write quicker than others, I'm on the slow side. And you do have a sentence that you have to write at the end of this particular quiz. Let me say today is M&M Day. I do have a big sack of M&Ms here, and I have some instructions for you. Wait, where are my instructions? Here they are. They're right here. So I'm going to pass the sack around, and let me just explain what's in the sack so that you know what to expect. There are peanut M&Ms. There are just a minute. I know that there's some plain. Here we go. Plain M&Ms, and then there's Reese's Pieces. So if you're allergic to chocolate, I got you covered. So there it is. You can grab what you like, and then send it around. We aren't going to use this for a little bit, so but you have time to take what you like and then send it around. You can send it over there. It doesn't matter. I don't care. Oh, look at that, Zoe. You're going to be last. Sorry. I tried. Oh yeah, but don't open it. Don't open the bag. You can look at them. Yeah, I don't want you all sugared up this early in class. At the end of class, that's fine. You can get all jacked up before your next class. But yeah, don't open them yet. Yeah, I guess if you're done with the quiz, then I can take your quiz. What's wrong? Are you complaining about my email? Yeah, you did that. No, for everybody. You can have two other people first. You don't do that? Okay, she just chose it for you. Okay. All right. Wow, look at you, good job. Are you ready? She's making a drawing? Okay, that's fine. I like it. All right, so what's the situation? How are we doing? Do I have all the quizzes? All right, yeah. One more, sorry. Thank you. Okay, let's take a look at what I got. So yes, just pass that around. We're going to use it in a bit, but give me a few minutes to go over like what we're going to be doing with it. Okay, first of all, the claim: higher proportion of video game players are truant than other normal people. So it's P1 is greater than P2. Hopefully you got that. Okay, so next we have the null and alternative hypotheses. So there it is. The alternative always is the one without the equal sign. So I should have written down the opposite of the claim, but I kind of wrote it down here, so there it is. This is right-tailed. Everyone should have right-tailed because of the way that I set up my, you can hardly read mine because it got garbled, but you got the picture. The test statistic was easy. It's Z, that 4.681. The p-value was 0. Now, it was kind of I was bothered by this because apparently when I wrote this quiz, I decided to round. So I wanted to just show you what the actual p-value was. So I typed all those in. Here's the actual p-value. And you know what that E means? Yes, that's it. I know, scientific notation people are like, no, it means 10 to the negative 6. Okay, the scientists, you're good with that. That's fine. But all the rest of us just think, oh, it's an extreme number. It's extremely small. So that might as well be 0. So that's why on the quiz, you'll see that I just put 0 down. Where is my quiz again? There it is. So you'll notice that I just rounded that to 0.000. So it's a right-tailed test. Decision is reject the null hypothesis because that is less than alpha. Was alpha given? Yes, it was. Alpha was 0.01. And so there is, look at my horrible handwriting, there is evidence to suggest that the proportion of video game players who are truant is greater than the proportion of normal people who are truant. Okay, I don't think it says normal, does it? Non-video game players. Whatever, you get the picture. All right, any questions about that? Okay, so you can look forward to this on the test in a week and a half. It's going to be easy, I'm sure. You're not going to have trouble with it. So that's that. We need to move on, though, because you're you're going to have those M&Ms melted in your hands through the bag if I'm not careful. You have these instructions, but before we do those instructions, I need to mention what we're doing today. We're doing a test called the chi-squared test. The chi-squared test is a test that allows you to compare nominal variables. These are variables that are categorical, so categorical variables. And so I've got several, you can choose. You don't have to just pick at random, you know. But anyway, so you can, you've got, some of you have peanut M&Ms, some of you have plain M&Ms, some of you have Reese's Pieces, because I thought that would be nice to have some non-chocolate in case you have a problem with chocolate. Thank you so much. So anyway, those are categorical variables. Here are my Reese's Pieces. Not only that, but once you have your bag, you'll notice that they come in multiple colors. So the Reese's Pieces have the colors orange, brown, and yellow. M&Ms, they have more colors. So you've got blue and red mixed in. You know, when I was a kid, they got rid of red for a bit. I don't know if you heard about this, but people freaked out that red food coloring caused cancer. And so they got rid of the red M&Ms for like a decade. And then in the 90s, they brought them back. It was such a joyful time because red's my favorite color. But anyway, you've got different colors. Those are like categories, and we want to compare the different categories. So before we go on, though, I should mention that the chi-squared test, the chi-squared test is a test that has, it's kind of like the t-test. You have lots of different degrees of freedom, so that the number of, the degrees of freedom. Oh, do we really want to see all this? I don't think so. Here, let's just say this, that the degrees of freedom that you have in your chi-squared test will change the way the chi-squared test looks. If you have a large number of degrees of freedom, the chi-squared distribution looks roughly like a normal distribution, but when you have a small number of degrees of freedom, it is very skewed. We're going to be dealing with small distributions here, small degrees of freedom. We're not going to compute this. Well, we can compute it on Excel, but for the most part, we're going to be using a table. So I need to just orient you to using tables because we haven't been using them up until now. It's not that difficult. So this is the chi-squared test statistic, the table for it. These are values that are called the critical values. I don't know if you've noticed this, but if your t-statistic, for example, on this quiz, if your test statistic is really big, like here, the test statistic is 4.68, I hope that at least some of you, when you saw that 4.68, you thought, oh yeah, we're definitely rejecting the null hypothesis here. Like if your test statistic is really big, it means you've gone too far away from what you could consider to be typical or to be just by chance. And you're way out there, way out there. And so whenever your test statistic is really big, that's what happens. And so this chi-squared thing, what they're doing is they're just saying, here's how big you need to be in order to reject the null hypothesis. So instead of looking at a p-value, we're kind of looking at a cutoff for the test statistic, the chi-squared value. We'll use this in just a bit, but let me help you with this to see how it works. You're going to do this yourselves in just a minute with your M&Ms or your Reese's Pieces. But for degrees of freedom 7, I'll explain what degrees of freedom are in the context of the problems we do. Degrees of freedom 7, find chi-squared for an alpha level. That 0.05 is your alpha level. So the alpha level of 0.05, so I go to 7, I go find 0.05, and there it is. That is the cutoff. If I compute my chi-squared test statistic, and if it's bigger than this, I will reject the null hypothesis. If it's less than this, I don't reject the null hypothesis. So this is like a cutoff, just like the p-value and the alpha level are a cutoff. But here, how big do you need to make this to make it seem amazing? Anything bigger than that is amazing. Okay, the other one, the other example here, if I'm trying to find degrees of freedom 6, and I want the alpha level of 0.005, which is really small, then that's this number here. Because notice that you're just going through the column and the row for those two things, so 18.548. So the one that we're going to be using today, the table is this table. I'll put this back up when we need it. First off, though, I need to explain how you compute the chi-square. Oh, no, first of all, we have to talk about the three flavors. The three flavors of chi-squared. Okay, where are they? Oh, yeah, here they are. I forgot to do this. So the three major flavors of chi-squared are the goodness of fit test. I'll explain. The test for independence, once again, I'll explain in a minute, and the test for homogeneity. Now, in terms of what we're going to do in here, today, we're going to learn how to compute this. These are actually surprisingly easy to calculate. So you can do this on a hand calculator. Literally, you're going to do it on a hand calculator in a minute. I have some handouts here. Okay, so we're going to do this today. That one we're going to do on Monday. And then the last one we're going to ignore and hope it goes away. So first, but I can't hope it goes away until after you do your homework for Monday because Newton wants it to be there. So so anyway. So goodness of fit. Let me see if I can explain goodness of fit in terms of the M&Ms. So where are my M&Ms? Here we are. So turns out that if you go on M&M Mars website, okay, this is not true anymore. Back in the late 90s, early 2000s, if you went on M&M Mars website, they would list the actual percentages of the colors in the different flavors of M&Ms. And this is the last time that I was able to get these numbers, which probably was in the early 2000s, like 2008 maybe. This is what they said. You can still go on the Internet Archive, like the waybackmachine.com or whatever it is, and you can actually find this information back in the web archive. But so these are the percentages that M&M Mars claims plain M&Ms have. So for example, yellow. Oh wait, where is it? Brown. Brown. 13% of all plain M&Ms are brown. 14% are yellow, 13% are red, and so on. So that's the claim. And so the goodness of fit test is when I take my bag of plain M&Ms and I look at it and I say, I don't know if that's a good fit for my bag of M&Ms. So goodness of fit, what you're doing is you're comparing a claim about a population with your sample. And so if my sample is not a good fit for this, one of several things could have happened. Either I cheated when I made this sample and it's not really random, or more likely, maybe M&Ms have changed the way that they color their M&Ms. I've read that M&Ms, the color distribution is chosen to make it the most appealing to people so that they'll eat as much as possible. And I guess that's the point of selling food, right? But anyway, so that's the goodness of fit test. You're comparing your sample to a particular given distribution. So the null hypothesis, and we'll do this, we'll practice this both with the M&Ms and with another example that's more boring. Anyway, we'll practice this. The population fits the given distribution. That's the null hypothesis. And then the population does not fit the given distribution is the alternative. So notice that it fitting the given distribution, that's the idea of the null hypothesis, which is also the no difference hypothesis. Difference. So no difference in the sense that there is no difference between the stated distribution, the percentages, and what my population really is. Okay, this looks scary, but it's not that bad. That is all we have to do to compute the chi-squared distribution. Okay, let me explain. First of all, that big sigma there, it means sum. You're adding up a bunch of junk. So what are you going to add up? You're going to add up your expected numbers minus the observed numbers squared divided by 2. Let me actually label these a little bit better. So this is expected. These are observed. And down here, of course, the E there is expected. But this is something that we could do quickly on Excel, but we could do it just as quickly with a hand calculator. So if you don't have a hand calculator, you can always pull out your phone and get the app, turn it on its side so it looks good, but we'll need a hand calculator here in just a minute. Before we do the M&Ms, though, I want to do a warm-up problem, a boring version. Oh, you know what we need to do, though, before we do that? Let me just mention the other two tests that are chi-squared tests, because they're going to be on your homework. Just multiple guess, you're not going to have to compute them. So the other two are the test for independence and the test for homogeneity. So test for independence, what that does is it asks the question, are two variables related or unrelated? For example, are color distribution and candy brand related or unrelated? Here is my M&Ms, and here are my Reese's Pieces. So what do you think? Is there a relationship between the brand of candy? Can you tell me, let me pick one out of here. Can you tell just by looking at it whether this is M&Ms or Reese's Pieces? You're incredible. Let me try one more. Let's see. You guys are amazing. Well, anyway, that's the idea behind a relationship. There's obviously a relationship between the brand of candy, whether it's M&Ms or Reese's Pieces, and the color distribution. You can just look at it. Even if I took out all of the red, green, and blue. If I took out all the red, green, and blue from the M&Ms, there is still a big difference. Do you notice? What do you notice? They're orange. Okay, what's that? No, come on. I'm not going to let you eat them. They aren't smaller. They're the same size. Do you need me to get my calipers out?
No.
Okay. Well, anyway. I think, though, that you can tell, well, we'll find out, there are a lot of oranges in there, whereas in M&Ms, there's, I don't know, it's not quite as many oranges. So even if I got rid of the reds and blues, I think you could tell which one was which. Okay, anyway, two variables are independent, meaning that they are unrelated. Here's another example of this, is, let's see, why can't I think of an example? What?
Like motorcycles and cars, they're both vehicles, but they both...
Oh, number of wheels or something, or the loudness factor? No, I have to have two qualitative variables. So qualitative variables, how about favorite color, and gender? Gender and favorite color? So guys, you're all blue, right?
No.
Okay, I'm just kidding. But anyway, so your favorite color and your gender, are they related? Those are two qualitative variables. Are they related or are they unrelated? So that's the test for independence. We'll do that Monday. And then the test for homogeneity, I only mention this because it's on your homework as one of the options for the multiple choice. So the distributions of the two populations are the same or different. So this would be like if I were to compare, here we go. I can't find peanut. There it is, peanut. Do peanut M&Ms and plain M&Ms, do they come, is it the same basic color distribution or not? So that's the sort of thing that the test for homogeneity means. And it is so similar for the test for independence that I find it to be unnecessary. So we don't go over that in full. Okay, so I have a piece of paper for you with some actual data, actual fudged data. I'll explain. Here, you can have this. So we have some actual data, and then you're going to fill in some data. But I did fudge this, so when I say actual, you should put quotes around it when you get the piece of paper. It's not actual data. Oh, that is lovely. You're welcome. There's too many. You can get one plate. I don't need one. I don't know. Oh, it's got all the extras. You've got tons of them. You only need one. Here, I'll take that one. Here. You want one, don't you? There you go. Here, you got extras. Why can't I count? Well, you got too many. What in the world? Why do I have so many? I don't have that many absentee today, do I? Okay. Oh, you've got one too. Incredible. Okay. Well, anyway, for those who are watching from home, is anyone watching from home? Just a minute. Yes, we are recording, so someone may be. Here's what we're all looking at. Wait, where is my actual data? Hold on a minute. Oh, wrong, just a minute. I have too many PowerPoints that all look alike. Just a sec, I gotta pull up the correct one. Just a sec. So it's not this one. Hold on, chi-squared. Where are we, chi-squared? That one maybe? Yes, this one. There it is. Okay, this is good. So what I have here is I have a little chart that I use to help me compute chi-squared. Now I have fudged the data very slightly. That is to say, instead of putting the actual data down, I discovered that our class has 34 students. Now I knew that actually ahead of time. And so I invented an extra student because I wanted to have 35 students. Now there's a reason why I wanted 35. I'll explain in a minute. So before we do this, let's first of all get some hypotheses. We're going to use this chart in just a minute. Here is my claim. My claim is that the population of statistics students are evenly distributed. No, it's not. It's not evenly distributed among the classes. That is to say that if you looked at the freshmen, sophomore, junior, seniors, and CCP, we have an inequity or an imbalance that it's not evenly distributed among those 5 groups. So first off, let's write down some hypotheses. So we have the claim here, we'll just leave that there. So hypothesis, the null hypothesis is that the percentages of CCP, freshmen, etc. are all 20%. Where am I getting 20%? Well, if we are evenly distributed, it means that 1/5 of you would be CCP, 1/5 of you would be freshmen, 1/5 of you would be sophomores, etc. throughout. So that's where I'm getting that 20%. And then the alternative hypothesis is that the percentages are not all 20%. Whew. Okay, so far so good? Okay, next we're going to compute, let's see, left, right, or two-tailed. There is no tail. Well, I shouldn't say it that way. All chi-square tests are right-tailed. Right-tailed, that's that way for you. So there is no, you don't have to worry about tails with chi-squared because they all go the same way. So we aren't going to worry about that. Trying to think what else. Test statistic is going to be a chi-squared distribution. Chi-squared. I suppose before we move on to computing the chi-squared test statistic, which we're going to do here, I should mention the degrees of freedom. So degrees of freedom, or DF, is equal to the categories minus 1. So take the number of categories. This is only for this particular test. So with the goodness of fit test, you take the number of categories, subtract 1, and you get the degrees of freedom. So for me, I have 5 categories, subtract 1, and that gives me 4 degrees of freedom. This will be important when we go back to look at these, get our critical value for this thing. Okay, getting back to this. Now you'll see why I chose to make you, invent a fake student here in just a minute. But let's go ahead and actually instantly, we will get this. So we will have, why do I care about it being 35 and not 34? Well, what we're going to do is these are the observed. So this is what I actually observed. I observed by looking at my class roster and counting. I counted 8 of you who were post-secondary. I counted 7 of you who are freshmen, 11 sophomores, 3 juniors. Okay, this is where I lie. There were only 2 juniors. I added 1 so that there could be 3. And then there were 6 seniors. So does that mean that things aren't evenly distributed if I took all of the statistics students on campus, put them together? I don't know. We're going to find out. Okay, so that's observed. This here is expected. F sub E is the way that I'm going to write expected. The expected frequency. Expected. There, I have to sound it out these days because it's getting hard to spell these. So anyway, so if you believe the null hypothesis, go back to the null hypothesis, the percentages are all 20%. In other words, 1/5, 1/5, 1/5. If you believe that, and if there are 35 of you, how many would you expect in each of these groupings? Easton?
7.
Why 7?
Because take 35 divided by 5, and that's the reason you add 1 because it was 34.
I didn't want to have a decimal, yes. So Easton has discovered why. It is okay to have a decimal here, I should say. So it's okay to have a fraction of a student. You can have 6.9 students in each category. I just didn't want to have to deal with a decimal student.
So is that like a student missing a foot or a hand or?
I can't talk about that because of the ADA compliance issues. So I will not, I'm not going there. But, although I guess by saying that, I probably just went there. Please don't report me to the Civil Rights Office. No, hopefully I haven't done a boo-boo. Actually, if I did, let me know and go report me, and I will have a chat with the Civil Rights Officer and find out how I can be a better person. Okay, getting back to this. There are the expected frequencies. How many do I expect? 7 of each. Now we're going to get into some math. So this, although the 7, that was a good math there. So we did 35 times 20%, and that gave me those numbers. Okay, next, we're going to subtract the observed minus the expected. Notice it says F sub O minus F sub E. And so I'm going to get 1 here. I'll get 0 here. This is 4. This one is -4. And this one is -1. So make sure it looks okay to you. It wasn't too bad. And now the next step is to square each of those. You know why we square them. It's because we're statisticians and we love to square things because we are squares. No, it's not because of that. It's because we want to make all of these negatives into positives. We've done this before when we did the standard deviation or the variance. We squared differences to make them positive. And it's so that when we average these together, we won't end up canceling stuff. We want to accumulate all the differences. And so square everything. That's going to be 1. This will be 0. This will be 16, 16, and 1. All right, that's not too bad. Okay, now for the hardest part, although it's not that bad, I'm going to divide each of these by its expected frequency. Now in this case, the expected frequencies are all 7. However, they don't all have to be the same in general. So for example, with this first one, I take the 1 divided by 7, and I'll get 0.1428 or whatever it is. I'm just going to leave it as 1/7. I'm more comfortable with fractions. And then I take the next one, that's 0. So let me just highlight that a different color. 0 divided by this 7, and I'll get 0/7. This is 16/7, 16, and 1/7. That wasn't too bad. Now for the final step, you'll notice that I blacked out this column here because this column is the total column, and I don't care about the total until the very bottom here. So I need to compute the total of all of these. So what is that? That's going to be 1, 16, 17, 34/7. 34/7. 34/7. Now I'll pull out my calculator. Let's do this one. Let's find out what 34/7 is. I got, whoa. Where's my glasses? It's It's really sad when you can't. Okay, phew. So that is 4.857. 4.857. There's my chi-squared test statistic. That was a lot of work. It wasn't that bad, was it? This, you know what I like about chi-squared is that it's not a black box. You know what I mean by black box is that you, like in Excel, you take your data and you throw it into the box there, and then out the other side, you get, oh, here's my p-value. It's like, how did that happen? I don't know. Don't really care. But here, you can kind of see what's going on. You can see that you've got this difference. The bigger the difference is here, the bigger this number will be, which will make this bigger, and that will make this bigger. So if you have big differences, it'll cause this to be big. If you have small differences, this will be small. But anyway, that is my chi-squared value, 4.857. Let me go back here. Uh-oh. I wish I could scroll. I'm just going to put it up top. My chi-squared value is 4.857. Okay, so you don't get a p-value with this particular test. You could, if we went to Excel, if we used Excel, we could get a p-value, but we're not going to get a p-value. So what we're going to do is we're going to look up the critical value, chi-squared, and this is going to be how many degrees of freedom? We determined that down at the bottom, 4 degrees of freedom. So let's see, how do I write this? I guess I'll just write it like this. Chi-squared of 0.05 for 4 degrees of freedom. How about that? Okay, so let's look this up on my table. I'm going to have to go back to my other here's what I'll do. I'll just pull this up right here. I think I've got it. I have 2 separate PowerPoints, and I should have just had one. There it is. Okay, so we have 4 degrees of freedom. Chi-squared of 0.05 is 9.488. I'm going to write this down, and then I'll show you what I've written. 9.488. Okay. So there it is. Nope. There it is. Yes. Okay, so my chi-squared, this is the critical value, and this is my actual test statistic. Remember what I said about critical values is that here we want to get bigger than that. So this is smaller. My chi-squared value, this one is smaller. So smaller, which means that we're going to fail to reject the null hypothesis. So I know that this feels like a shift. We're doing something different here, but if you think of it in terms of trying to figure out how extreme the data is, the bigger the chi-squared value, it means the more spread out your data is, the more extreme it is. And so this smaller just means we're going to fail to reject the null hypothesis. And so there is not enough evidence to suggest that the population of statistics students is not evenly distributed. So even though you can clearly see, even with my fudged data, where is it? There it is. I mean, it's pretty spread out. You've got very few juniors. Maybe if I left it at 2, then you'd have a better distribution here. But there's a lot of sophomores. I would guess that that's the most popular usually anyway. So when we say that there's not enough evidence to suggest the alternative hypothesis, one thing we could do is we could go gather more evidence. I mean, imagine if you were a detective working to try to, gather evidence to, convict someone of murder, and the DA says, hey, you don't have enough evidence to charge this person yet. Well, then you'd go and gather more evidence. So you could get more evidence by getting a larger sample and then run the test again. Okay, so speaking of larger samples, you have at the bottom of your sheet the M&Ms. So this one you can do yourselves. I'm going to do it for my stuff here, so you can see what I've got. Here it is. So if you're watching from home, sorry, I do have M&Ms for you, but they'll get eaten before Monday, so sorry about that. But anyway, I put them in bags for a couple of reasons. I should have mentioned this. Hold on a minute. This is in my other PowerPoint. Sorry. Let's just, let's see, give me a sec here. Go back up here. There it is. Okay, so this is a photo, almost, here we go. So this is a photo of what my kitchen table looked like 2 years ago, okay? I didn't bother taking photos last night. It was basically the same though. So you can see here, we have some gloves to keep you safe from whatever disease I might have. We have a little scoop, which is gonna be the serving size, 1/8 of a cup. Sorry guys, I'm not gonna buy 15 pounds of M&Ms for you. And then, hazelnut, apparently, 2 years ago, I have the Reese's Pieces just to compare because I was curious. So, and instead of snack bags, I have regular because they were cheaper. Anyway, so that's what we have at least 2 years ago, and then I did this, and now you see the result. So anyway, I show you that just to mention that when we get done with this, you can feel confident that your M&Ms or your Reese's Pieces or whatever you've got there, they are safe to consume or save for later or give to your friend, or if you really don't want them, just put them up here and I'll give them to my next class. So whatever the situation is, they are safe. So you've probably already finished. I need to do mine, but everyone's going to have a different set of numbers here, though. So if you're confused about what to do, first step is to count up each of your colors and write them into your little grid at the bottom of your handout. So give me a minute here, and I'm going to do the same. So 1, 2. I saw some of you were clever and had them all separated. I can't do that. 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 21. Okay. Okay, so here's what I got. You probably got something very different from me. Mine, by the way, was I'm doing Reese's. Are there 2 E's first? Okay, however many E's. You decide.
All the E's.
You decide how many E's you want in there, and I'm happy. So anyway, you'll have your own numbers. You'll have your own total. And what we're testing, by the way, is we're testing the claim that M&Ms, or in this case, it's going to be the Reese's Pieces, have an even color distribution. Now, I know I just showed you that information from 2008 that said that M&M's Mars claims that there is not an even color distribution, but we're going to assume that they're an even color distribution. In other words, you should expect one, you know what, this is Reese's. Let's not, I'm going to eliminate these from me because I have Reese's. If you have M&M's, don't do this. So this is just because this is Reese's. Okay, so for me, and for anyone else who chose Reese's, and if you chose Reese's, you're going to be happy because you have less calculating to do. What you're going to do is you're going to test the claim that they're all the same. That is, all colors are produced with the same frequency or proportion. In other words, to get my expected frequencies, I'm going to take the total and divide by 3. When I take 31 and divide by 3, I get 10.33. And you'll get whatever number you get. If you have a number that's a multiple of 3, you're going to be so happy because no decimals. Now, if you were an M&M person, then you're going to test a slightly different thing. You're going to take your total and divide it by 6 because there are, at least theoretically, there are 6 categories that M&Ms supposedly have. And I believe if you look at, take enough bags, you'll find all 6 of those colors This bag has all 6 colors. So red, orange, yellow, green, blue, and brown. So if you really want one, I got that. It's all 6 colors. So if you're an M&M person, divide by 6 to get your expected. If you're a Reese's person, just divide by 3. Now the rest of this, we do exactly what we did back here, and that is subtract, square your numbers, divide by the expected, and then add them up. So I'm going to do the same up here. I'll be quiet for a minute so that you can take your time. If you have questions, though, I'll take them in a minute. Okay, I'm done, so if you're confused, I can come around and help you do your calculation. If you're not confused, then you can go to it. Oh, by the way, I should have mentioned this earlier, that if you need that sugar rush, now is the time where you could take and eat. These are your M&Ms. Yes? We'll get there.
Okay.
Yeah, we will need them. But in terms of the data, once you've got your colors written down, you can gobble them all up if you need to. So whatever you need, if it helps you, feel free. All right, let's finish this up. So let's see if I back up this thing. There we go. So if you had Reese's Pieces, degrees of freedom will be categories minus 1. So you had 3 categories, orange, yellow, brown. Subtract 1 and you get degrees of freedom 2. So if you're Reese's Pieces, this is your number. That's the thing to beat, 5.991. So that's mine. Now, if you are an M&M person, you have 6 categories. Subtract 1, that's 5 degrees of freedom. So that means you're here, and the number to beat is 11.07. So that's what you want to compare yours to. You can jot it down if you want. That's called the critical value for this test. Just a minute. I'm going to write this here so I can compare. 5.991 is me. And if you're an M&M person, it's 11.07. Now remember, if your test statistic, in this case mine is right here, if your test statistic, this number, that's the total of all of these, if that number is bigger than that, then you reject the null hypothesis, and the conclusion is that there is evidence to suggest that your candy is produced with something other than an even distribution of, like, they're not all the same. So there's pretty strong evidence for me with my Reese's Pieces. In fact, I'm guessing that most of the Reese's Pieces people got a pretty big chi-squared value, because there are a lot of oranges in these bags. I noticed that when I was spooning them out. It's like oranges, Just lots of oranges. What about the M&Ms though? Did anyone with an M&M thing have a chi-squared value down here bigger than 11.07? Oh, you did? Are you peanut or plain? Peanut. Okay, so you must have had like missing a bunch of colors, right? You had how many? 7 green. Wow. So yeah, that was so just by the look of the draw, just by chance, Noel ended up with a lot of greens. And I remember this as I was scooping them out. I'm like, well, there's a bunch of, like some of you, there were a couple of bags that were heavy with one color, like red or something. It's like, well, nothing I can do about that. I'm sampling them carefully. Oh, I guess I did do one thing. I should, just in the interest of full disclosure. When I was scooping out the peanut M&Ms, because they're so big, I did actually make sure that there were exactly 12 in each bag. So I don't know if anyone got something other than 12, it meant that I can't count, or at least it was so late. You know, it's probably 8 o'clock at night when I did this, so things were getting a little fuzzy. But anyway, so here's what I'd like you to do though. So now that we've done this, hopefully you've got your results. So most of you with the M&Ms, probably you failed to reject the null hypothesis, and the conclusion is that there isn't any evidence to suggest that M&Ms, have some color distribution other than just a straight flat 1/6 of every color. And Reese's, probably it was the opposite, that we're all greater than the critical value. But what I'm interested in is I want to see your data, so I'm asking you to help me out because we're going to use this on Monday. So share your results with me, please, if you would. I have 2 ways you can do this. Either you can just scan that, or you can type that into your phone, and either way you'll get to my little survey. Oh, do both of those go to the same survey? You better scan, well here, I'll double check that the bottom one. Hold on a minute. The bottom one might be an old survey. I should have checked. Oh yeah, MV, NU, I'll explain. MS. Let's see. Oh, it says 2019. Oh no, hold on a minute. Okay, how about this? I'll figure out if you type this, you'll get the 2019 one, which apparently I did hazelnut. If you chose the Reese's Pieces, then select hazelnut. But if you scan this, you'll get the up-to-date version of this. I don't know why there's... Oh, what in the world? Why? Just a minute. Maybe I need to do something on my end. Hold on a sec. Don't do it yet. Don't do it. Oh, you did it already?
Some of us did, yeah.
Well, you can do it again. Just give me a sec.
Okay.
Forms. Maybe I have to publish the form?
Yes.
Hold on. Let's see. Where's MM? Oh, here it is. Oh, crud. Why is it? Okay, I guess that, yeah, you're just going to have to, I don't know why I don't have the right link. If you have the Reese's Pieces, choose hazelnut on the list there, and I'll figure it out. So, and then enter your numbers of each color, and then go and enjoy. And if you don't want your M&Ms, give them to a friend, or put them up here and I'll give them to the next class. Either way is fine. So we're all set. Hope you have a great weekend, and I will bring the collected data on Monday. You don't want 19, okay. Excellent.
I'm not trying to get you like in trouble with like HR or
Oh, yeah,
anything,
yeah.
it's just, in my old school, I wouldn't do like percentages of people because it's kind of like,
Oh, yeah.
you can't have like a third of a person.
Oh, no, but in statistics you can.
In statistics, yes.
And you have to, for the statistics to work out. So when you do this, yeah, we wouldn't do a third of a person, even if we're, yeah.
Let's not think about it too
Yeah,
hard.
we don't think about that. But in terms of the way that this calculation works, you have to do it as a decimal. You have to do, yeah.
So
like,
you can't round
Yeah,
them.
you can't round it until the very end, yeah.
Yeah.
At the very end you can round, but you can't round before that.
The project videos up yet?
They are, they've been up since yesterday. I put them up yesterday morning, I believe, unless I did the same thing as I did with this.
Well, last time I checked, it's still up there, so.
It's up there still?
Yeah, I'll be monkeying with that this weekend.
Excellent. They're easy. Thanks for reminding me. Whew. Onward.
Yep.
Are you coming to the zombie apocalypse tomorrow?
I am not.
Yeah, you could be a zombie.
I don't do zombie.
Oh, that's unfortunate. One day.
One day soon I will be. Yeah. Jesus is coming. Save me from the apocalypse. Amazing.
I think the surveys to be a zombie in it, and I purposely didn't take that honor seminar, so I didn't have to do the survival thing, so I definitely don't want to be a zombie.
Yeah, exactly. Like, I don't know. Some people are really into that sort of thing.
Not.
I'm not. It doesn't seem like fun. Yeah, I think I'd be the same way. I would purposefully not take that seminar.
Yeah, it looked fun other than that. Like, I don't want to spend a whole day distracted, or like whatever the time period is distracted because there's people or zombies after me.
Yeah. Okay.
Have a good weekend.
Yeah, we'll see you later. Welcome. Shorts today with a sweatshirt.
It was raining this morning.
Okay.
Yeah, it was kind of
Oh. Last class, we can do this.
We can make it shorter.
I would feel bad for you. We don't want to rip you off.